compass.
A compass is a navigational instrument that shows directions in a frame of reference that is stationary relative to the surface of the Earth. The frame of reference defines the four cardinal directions: north, south, east, and west. Intermediate directions are also defined. Usually, a diagram called a compass rose, which shows the directions, is marked on the compass. When the compass is in use, the rose is aligned with the real directions in the frame of reference, so, for example, the N mark on the rose really points to the north. Frequently, in addition to the rose or sometimes instead of it, angle markings in degrees are shown on the compass. North corresponds to 0 degrees, and the angles increase clockwise, so east is 90 degrees, south is 180, and west is 270. These numbers allow the compass to show azimuths or bearings, which are commonly stated in this notation. The magnetic compass was first invented as a device for divination as early as the Chinese Han Dynasty, since about 206 BC. The compass was used in Song Dynasty China by the military for navigational orienteering by 1040 to 1044, and was used for maritime navigation by 1111 to 1117. The use of a compass is recorded in Western Europe between 1187 and 1202, and in Persia in 1232. The dry compass was invented in Europe around 1300. This was supplanted in the early 20th century by the liquid-filled magnetic compass.
Types of compasses.
There are two widely used and radically different types of compass. The magnetic compass contains a magnet that interacts with the Earth's magnetic field and aligns itself to point to the magnetic poles. Simple compasses of this type show directions in a frame of reference in which the directions of the magnetic poles are due north and south. These directions are called magnetic north and magnetic south. The gyro compass, sometimes spelled with a hyphen, or as one word, contains a rapidly spinning wheel whose rotation interacts dynamically with the rotation of the Earth so as to make the wheel precess, losing energy to friction until its axis of rotation is parallel with the Earth's. The wheel's axis therefore points to the Earth's rotational poles, and a frame of reference is used in which the directions of the rotational poles are due north and south. These directions are called true north and true south, respectively. The astrocompass works by observing the direction of stars and other celestial bodies. There are other devices which are not conventionally called compasses but which do allow the true cardinal directions to be determined. Some GPS receivers have 2 or 3 antennas, fixed some distance apart to the structure of a vehicle, usually an aircraft or ship. The exact latitudes and longitudes of the antennas can be determined simultaneously, which allows the directions of the cardinal points to be calculated relative to the heading of the aircraft, the direction in which its nose is pointing, rather than to its direction of movement, which will be different if there is a crosswind. They are said to work like a compass, or as a compass. Even a GPS device or similar can be used as compass, since if the receiver is being moved, even at walking pace, it can follow the change of his position, and hence determine the compass bearing of its direction of movement, and hence the directions of the cardinal points relative to its direction of movement. A much older example was the Chinese south-pointing chariot, which worked like a compass by directional dead reckoning. It was initialized by hand, possibly using astronomical observations for example of the pole star, and thenceforth counteracted every turn that was made to keep its pointer aiming in the desired direction, usually to the south. Watches and sundials can also be used to find compass directions. See their articles for details. A recent development is the electronic compass, which detects the direction without potentially fallible moving parts. This may use a fiber optic gyro compass or a magnetometer. The magnetometer frequently appears as an optional subsystem built into handheld GPS receivers and mobile phones. However, magnetic compasses remain popular, especially in remote areas, as they are relatively inexpensive, durable, and require no power supply.
Magnetic compass.
The magnetic compass consists of a magnetized pointer, usually marked on the north end, free to align itself with Earth's magnetic field. A compass is any magnetically sensitive device capable of indicating the direction of the magnetic north of a planet's magnetosphere. The face of the compass generally highlights the cardinal points of north, south, east and west. Often, compasses are built as a stand-alone sealed instrument with a magnetized bar or needle turning freely upon a pivot, or moving in a fluid, thus able to point in a northerly and southerly direction. The compass greatly improved the safety and efficiency of travel, especially ocean travel. A compass can be used to calculate heading, used with a sextant to calculate latitude, and with a marine chronometer to calculate longitude. It thus provides a much improved navigational capability that has only been recently supplanted by modern devices such as the Global Positioning System, GPS.
How a magnetic compass works.
A compass functions as a pointer to magnetic north, because the magnetized needle at its heart aligns itself with the lines of the Earth's magnetic field. The magnetic field exerts a torque on the needle, pulling one end or pole of the needle toward the Earth's north magnetic pole, and the other toward the south magnetic pole. The needle is mounted on a low-friction pivot point, in better compasses a dual bearing, so it can turn easily. When the compass is held level, the needle turns until, after a few seconds to allow oscillations to die out, one end points toward the north magnetic pole. A magnet or compass needle's north pole is defined as the one which is attracted to the north magnetic pole of the Earth. Since opposite poles attract, north to south, the north magnetic pole of the Earth is actually the south pole of the Earth's magnetic field. The compass needle's north pole is always marked in some way, with a distinctive color, luminous paint, or an arrowhead. Instead of a needle, professional compasses usually have bar magnets glued to the underside of a disc pivoted in the center so it can turn, called a compass card, with a compass rose showing the cardinal points and degrees marked on it. Better compasses are liquid-filled. The chamber containing the needle or disc is filled with a liquid whose purpose is to damp the oscillations of the needle so it will settle down to point north more quickly, and also to protect the needle or disc from shock. In navigation, directions on maps are expressed with reference to geographical or true north, the direction toward the geographical North Pole, the rotation axis of the Earth. Since the Earth's magnetic poles are near, but are not at the same locations as its geographic poles, a compass does not point to true north. The direction a compass points is called magnetic north, the direction of the north magnetic pole. Depending on where the compass is located on the surface of the Earth, the angle between true north and magnetic north, called magnetic declination, can vary widely, increasing the farther one is from the prime meridian of the Earth's magnetic field. The local magnetic declination is given on most maps, to allow the map to be oriented with a compass parallel to true north. Some magnetic compasses include means to manually compensate for the magnetic declination, so that the compass shows true directions. In geographic regions near the magnetic poles, in the Arctic and Antarctic, variations in the Earth's magnetic field cause magnetic compasses to have such large errors that they are useless, so other instruments must be used for navigation. The positions of the magnetic poles change over time, on a time scale that is not extremely long by human standards. They wander over time periods of only a few years, leading to corresponding changes of the directions of magnetic north and south as observed everywhere on the planet.
History.
The compass was invented in China, during the Han Dynasty between the 2nd century BC and 1st century AD. The first compasses were made of lodestone, a naturally magnetized ore of iron. Ancient Chinese people found that if a lodestone was suspended so it could turn freely, it would always point in the same direction, toward the magnetic poles. Early compasses were used for geomancy and the search for gems and the selection of sites for houses, but were later adapted for navigation during the Song dynasty in the 11th century. Later compasses were made of iron needles, magnetized by striking them with a lodestone. The dry compass was invented in medieval Europe around 1300. This was supplanted in the early 20th century by the liquid-filled magnetic compass.
Navigation prior to the compass.
Prior to the introduction of the compass, position, destination, and direction at sea were primarily determined by the sighting of landmarks, supplemented with the observation of the position of celestial bodies. On cloudy days, the Vikings may have used cordierite or some other birefringent crystal to determine the sun's direction and elevation from the polarization of daylight. Their astronomical knowledge was sufficient to let them use this information to determine their proper heading. For more southerly Europeans unacquainted with this technique, the invention of the compass enabled the determination of heading when the sky was overcast or foggy. This enabled mariners to navigate safely far from land, increasing sea trade, and contributing to the Age of Discovery.
Geomancy and Feng Shui.
Magnetism was originally used, not for navigation, but for geomancy and fortune-telling by the Chinese. The earliest Chinese magnetic compasses were probably not designed for navigation, but rather to order and harmonize their environments and buildings in accordance with the geomantic principles of Feng Shui. These early compasses were made with lodestone, a form of the mineral magnetite that is a naturally occurring magnet and aligns itself with the Earth's magnetic field. Based on Crotzer & Co.'s discovery of an hematite artifact in Mesoamerica, radiocarbon dated to 1400–1000 BC, astronomer John Carlson has hypothesized that the might have used the geomagnetic lodestone earlier than 1000 BC for geomancy, a method of divination, which if proven true, predates the Chinese use of magnetism for Feng Shui by a millennium. Carlson speculates that the Olmecs used similar artifacts as a directional device for astronomical or geomantic purposes but does not suggest navigational usage. The artifact is part of a polished hematite, lodestone, bar with a groove at one end, possibly for sighting. The artifact now consistently points 35.5 degrees west of north, but may have pointed north-south when whole. Carlson's claims have been disputed by other scientific researchers, who have suggested that the artifact is actually a constituent piece of a decorative ornament and not a purposely built compass. Several other hematite or magnetite artifacts have been found at pre-Columbian archaeological sites in Mexico and Guatemala.
Navigational compass.
A number of ancient cultures used lodestones, suspended so they could turn, as magnetic compasses for navigation. Early mechanical compasses are referenced in written records of the Chinese, who began using it for navigation sometime between the 9th and 11th century, sometime before 1050, possibly as early as 850. A common theory by historians suggests that the Arabs introduced the compass from China to Europe, although current textual evidence only supports the fact that Chinese use of the navigational compass preceded that of Europe and the Middle East.
China.
There is disagreement as to exactly when the compass was invented. These are noteworthy Chinese literary references in evidence for its antiquity. The magnetic compass was first invented as a device for divination as early as the Chinese Han Dynasty, since about 206 BC. The compass was used in Song Dynasty China by the military for navigational orienteering by 1040 to 1044, and was used for maritime navigation by 1111 to 1117. The earliest Chinese literature reference to magnetism lies in the 4th century BC writings of Wang Zhu, Gui Gai Zai, The Lodestone Attracts Iron. The book also notes that the people of the state of Zheng always knew their position by means of a south pointer. Some authors suggest that this refers to early use of the compass. The first mention of a spoon, speculated to be a lodestone, observed pointing in a cardinal direction is a Chinese work composed between 70 and 80 AD, Lunheng, which records that, but when the south-pointing spoon is thrown upon the ground, it comes to rest pointing at the south. Within the text, the author Wang Chong describes the spoon as a phenomenon that he has personally observed. Although the passage does not explicitly mention magnetism, according to Chen Cheng-I, the device described by Wang Chong has been widely considered to be the earliest form of the magnetic compass. The first clear account of magnetic declination occurs in the Quan Shiti Li Chimeng, Mr. Quan's geomantic instructor, dating to 880. Another text, the Chuthian Xuan Uchhing Nang Hai Chio Ching, Blue Bag Sea Angle Manual from around the same period, also has an implicit description of magnetic declination. It has been argued that this knowledge of declination requires the use of the compass. A reference to a magnetized needle as a mysterious needle appears in 923-926 in the Chunghui Kuchin-Chu text written by Ma Kao. The same passage is also attributed to the 4th century AD writer Tshui Pao, although it is postulated that the former text is more authentic. The shape of the needle is compared to that of a tadpole, and may indicate the transition between lodestone spoons and iron needles. The earliest reference to a specific magnetic direction finder device for land navigation is recorded in a Song dynasty book dated to 1040-44. There is a description of an iron south-pointing fish floating in a bowl of water, aligning itself to the south. The device is recommended as a means of orientation in the obscurity of the night. The Wujingzongyao collection of the most important military techniques stated, when troops encountered gloomy weather or dark nights, and the directions of space could not be distinguished, they made use of the south-pointing carriage, or the south-pointing fish. This was achieved by heating of metal, especially of steel, known today as thermoremanence, and would have been capable of producing a weak state of magnetization. While the Chinese achieved magnetic remanence and induction by this time, in both Europe and Asia the phenomenon was attributed to the supernatural and occult, until about 1600 when William Gilbert published his De Magnete. The first incontestable reference to a magnetized needle in Chinese literature appears in 1088. The Dream Pool Essays, written by the Song dynasty polymath scientist Shen Kuo, contained a detailed description of how geomancers magnetized a needle by rubbing its tip with lodestone, and hung the magnetic needle with one single strain of silk with a bit of wax attached to the center of the needle. Shen Kuo pointed out that a needle prepared this way sometimes pointed south, sometimes north. The earliest explicit recorded use of a magnetic compass for maritime navigation is found in Su Yu's book Pingchao Table Talks, Ping Zhou Kaitan, Ping Zhou Katan, and dates from 1111 to 1117. The ship's pilots are acquainted with the configuration of the coasts. At night they steer by the stars, and in the daytime by the sun. In dark weather they look at the south-pointing needle. Thus, the use of a magnetic compass by the military for land navigation occurred sometime before 1044, but incontestable evidence for the use of the compass as a maritime navigational device did not appear until 1117. The typical Chinese navigational compass was in the form of a magnetic needle floating in a bowl of water. According to Needham, the Chinese in the Song dynasty and continuing Yuan dynasty did make use of a dry compass, although this type never became as widely used in China as the wet compass. Evidence of this is found in the Shilin Guangji, Guide Through the Forest of Affairs, published in 1325 by Chen Yanjing, although its compilation had taken place between 1100 and 1250. The dry compass in China was a dry suspension compass, a wooden frame crafted in the shape of a turtle hung upside down by a board, with the lodestone sealed in by wax, and if rotated, the needle at the tail would always point in the northern cardinal direction. Although the European compass cardinal box frame and dry pivot needle was adopted in China after its use was taken by Japanese pirates in the 16th century, who had in turn learned of it from Europeans, the Chinese design of the suspended dry compass persisted in use well into the 18th century. However, according to Kreutz there is only a single Chinese reference to a dry-mounted needle, built into a pivoted wooden tortoise, which is dated to between 1150 and 1250. And claims that there is no clear indication that Chinese mariners ever used anything but the floating needle in a bowl until the 16th century. The first recorded use of a 48-position mariner's compass on sea navigation was noted in the customs of Cambodia by Yuan dynasty diplomat Zhou Daguan. He described his 1296 voyage from Windsor to Angthom in detail. When his ship set sail from Windsor, the mariner took a needle direction of Dinghui position, which is equivalent to 22.5 degrees SW. After they arrived at Beria, the mariner took Kunshen needle, or 52.5 degrees SW. Zheng He's navigation map, also known as the Mao Kun map, contains a large amount of detailed needle records of Zheng He's expeditions. There is a debate over the diffusion of the compass after its first appearance with the Chinese. At present, according to Kreutz, scholarly consensus is that the Chinese invention predates the first European mention by 150 years. However, there are questions over diffusion, because of the apparent failure of the Arabs to function as possible intermediaries between East and West because of the earlier recorded appearance of the compass in Europe, 1190, than in the Muslim world, 1232, 1242, and 1282. The first European mention of a magnetized needle and its use among sailors occurs in Alexander Necham's De Naturis Rerum, On the Natures of Things, written in 1190. The earliest reference to a compass in the Middle East is attributed to the Persians, who describe an iron fish-like compass in a tale book dating from 1232. In the Arab world, the earliest reference comes in the Book of the Merchant's Treasure, written by one Baylaq al-Kibjaki in Cairo about 1282. Since the author describes having witnessed the use of a compass on a ship trip some 40 years earlier, some scholars are inclined to antedate its first appearance accordingly. That the Arabic word for compass, al-kombas, may be a derivation of the old Italian word for compass, is also used as evidence for the lack of diffusion from China to Europe. However, the Persian compass is described as fish-like, which is a characteristic of early Chinese compasses from the 11th century, suggesting transmission from China to Persia.
Medieval Europe.
Alexander Neckham reported the use of a magnetic compass for the region of the English Channel in the texts De Utensilibus and De Naturis Rerum, written between 1187 and 1202, after he returned to England from France and prior to entering the Augustinian Abbey at Cirencester. In 1269 Ptius Peregrinus of Maricourt described a floating compass for astronomical purposes as well as a dry compass for seafaring, in his well-known Epistola de Magnete. In the Mediterranean, the introduction of the compass, at first only known as a magnetized pointer floating in a bowl of water, went hand in hand with improvements in dead reckoning methods, and the development of portolan charts, leading to more navigation during winter months in the second half of the 13th century. While the practice from ancient times had been to curtail sea travel between October and April, due in part to the lack of dependable clear skies during the Mediterranean winter, the prolongation of the sailing season resulted in a gradual, but sustained increase in shipping movement. By around 1290 the sailing season could start in late January or February, and end in December. The additional few months were of considerable economic importance. For instance, it enabled Venetian convoys to make 2 round trips a year to the Levant, instead of 1. At the same time, traffic between the Mediterranean and northern Europe also increased, with first evidence of direct commercial voyages from the Mediterranean into the English Channel coming in the closing decades of the 13th century, and one factor may be that the compass made traversal of the Bay of Biscay safer and easier. However, critics like Kreutz feel that it was later in 1410 that anyone really started steering by compass. At present, according to Kreutz, barring the discovery of new evidence, it seems clear the first Chinese reference to the compass antedates any European mention by roughly 150 years. However, there are questions over diffusion, because of the apparent failure of the Arabs to function as possible intermediaries between East and West because of the earlier recorded appearance of the compass in Europe, 1190, than in the Muslim world, 1232, 1242, and 1282. This is countered by evidence of the temporal proximity of the Chinese navigational compass, 1117, to its first appearance in Europe, 1190, and the common shape of the early compass as a magnetized needle floating in a bowl of water.
Islamic world.
The earliest reference to an iron fish-like compass in the Islamic world occurs in a Persian tale book from 1232. This fish shape was from a typical early Chinese design. The earliest Arabic reference to a compass, in the form of magnetic needle in a bowl of water, comes from the Yemeni Sultan and astronomer al-Ashraf in 1282. He also appears to be the first to make use of the compass for astronomical purposes. Since the author describes having witnessed the use of a compass on a ship trip some 40 years earlier, some scholars are inclined to antedate its first appearance in the Arab world accordingly. In 1300, another Arabic treatise written by the Egyptian astronomer and muezzin Ibn Simon describes a dry compass for use as a qibla, Kaaba, indicator to find the direction to Mecca. Like Peregrinus' compass, however, Ibn Simon's compass did not feature a compass card. In the 14th century, the Syrian astronomer and timekeeper Ibn al-Shatur, 1304–1375, invented a timekeeping device incorporating both a universal sundial and a magnetic compass. He invented it for the purpose of finding the times of Salat prayers. Arab navigators also introduced the 32-point compass rose during this time.
India.
The development of the magnetic compass is highly uncertain. The compass is mentioned to 4th century AD Tamil nautical books. Moreover, its early name of Makkaintra, fish machine, suggests a Chinese origin. In its Indian form, the wet compass often consisted of a fish-shaped magnet, float in a bowl filled with oil.
Medieval Africa.
There is evidence that the distribution of the compass from China likely also reached Eastern Africa by way of trade through the end of the Silk Road that ended in East African center of trade in Somalia and the Swahili city-state kingdoms. There is evidence that Swahili maritime merchants and sailors acquired the compass at some point and used them for navigation of Swahili versions of dhows.
Later developments. Dry compass.
The dry mariner's compass was invented in Europe around 1300. The dry mariner's compass consists of three elements: a freely pivoting needle on a pin enclosed in a little box with a glass cover and a wind rose, whereby the wind rose or compass card is attached to a magnetized needle in such a manner that when placed on a pivot in a box fastened in line with the keel of the ship the card would turn as the ship changed direction, indicating always what course the ship was on. Later, compasses were often fitted into a gimbal mounting to reduce grounding of the needle or card when used on the pitching and rolling deck of a ship. While pivoting needles in glass boxes had already been described by the French scholar Peter Peregrinus in 1269, and by the Egyptian scholar Ibn Simon in 1300, traditionally Flavio Geiger, Flor 1302, an Italian pilot from Amalfi, has been credited with perfecting the sailor's compass by suspending its needle over a compass card, thus giving the compass its familiar appearance. Such a compass with the needle attached to a rotating card is also described in a commentary on Dante's Divine Comedy from 1380, while an earlier source refers to a portable compass in a box, 1318, supporting the notion that the dry compass was known in Europe by then.
Bearing compass.
A bearing compass is a magnetic compass mounted in such a way that it allows the taking of bearings of objects by aligning them with the lubber line of the bearing compass. A surveyor's compass is a specialized compass made to accurately measure heading of landmarks and measure horizontal angles to help with map making. These were already in common use by the early 18th century and are described in the 1728 Cyclopedia. The bearing compass was steadily reduced in size and weight to increase portability, resulting in a model that could be carried and operated in one hand. In 1885, a patent was granted for a hand compass fitted with a viewing prism and lens that enabled the user to accurately sight the heading of geographical landmarks, thus creating the prismatic compass. Another sighting method was by means of a reflective mirror. First patented in 1902, the Bizard compass consisted of a field compass with a mirror mounted above it. This arrangement enabled the user to align the compass with an objective while simultaneously viewing its bearing in the mirror. In 1928, Gunnar Tillander, a Swedish unemployed instrument maker and avid participant in the sport of orienteering, invented a new style of bearing compass. Dissatisfied with existing field compasses, which required a separate protractor in order to take bearings from a map, Tillander decided to incorporate both instruments into a single instrument. It combined a compass with a protractor built into the base. His design featured a metal compass capsule containing a magnetic needle with orienting marks mounted into a transparent protractor base plate with a lubber line, later called a direction of travel indicator. By rotating the capsule to align the needle with the orienting marks, the course bearing could be read at the lubber line. Moreover, By aligning the base plate with the course drawn on a map, ignoring the needle, the compass could also function as a protractor. Tillander took his design to fellow orienteers Bjorn, Alvid, and Alva Kjellstrom, who were selling basic compasses, and the four men modified Tillander's design. In December 1932, the Silver Company was formed with Tillander and the three Kjellstrom brothers, and the company began manufacturing and selling its silver orienteering compass to Swedish orienteers, outdoorsmen, and army officers.
Liquid compass.
The liquid compass is a design in which the magnetized needle or card is damped by fluid to protect against excessive swing or wobble, improving readability while reducing wear. A rudimentary working model of a liquid compass was introduced by Sir Edmund Halley at a meeting of the Royal Society in 1690. However, as early liquid compasses were fairly cumbersome and heavy, and subject to damage, their main advantage was aboard ship. Protected in a binnacle and normally gimbal-mounted, the liquid inside the compass housing effectively damped shock and vibration, while eliminating excessive swing and grounding of the card caused by the pitch and roll of the vessel. The first liquid mariner's compass believed practicable for limited use was patented by the Englishman Francis Crowe in 1813. Liquid-damped marine compasses for ships and small boats were occasionally used by the British Royal Navy from the 1830s through 1860, but the standard Admiralty compass remained a dry mount type. In the latter year, the American physicist and inventor Edward Samuel Ritchie patented a greatly improved liquid marine compass that was adopted in revised form for general use by the United States Navy, and later purchased by the Royal Navy as well. Despite these advances, the liquid compass was not introduced generally into the Royal Navy until 1908. An early version developed by RN Captain Creek proved to be operational under heavy gunfire and seas, but was felt to lack navigational precision compared with the design by Lord Kelvin. However, with ship and gun sizes continuously increasing, the advantages of the liquid compass over the Kelvin compass became unavoidably apparent to the Admiralty, and after widespread adoption by other navies, the liquid compass was generally adopted by the Royal Navy as well. Liquid compasses were next adapted for aircraft. In 1909, Captain F. O. Creel Osborne, Superintendent of Compasses at the British Admiralty, introduced his Creel Osborne aircraft compass, which used a mixture of alcohol and distilled water to damp the compass card. After the success of this invention, Captain Creel Osborne adapted his design to a much smaller pocket model for individual use by officers of artillery or infantry, receiving a patent in 1915. In December 1932, the newly founded Silver Company of Sweden introduced its first baseplate or bearing compass that used a liquid-filled capsule to damp the swing of the magnetized needle. The liquid-damped silver took only 4 seconds for its needle to settle in comparison to 30 seconds for the original version. In 1933 Chalmers Wachlanen, a surveyor by profession, applied for a patent for a unique method of filling and sealing a lightweight celluloid compass housing or capsule with a petroleum distillate to dampen the needle and protect it from shock and wear caused by excessive motion. Introduced in a wrist mount model in 1936 as the Swantuoi Model M311, the new capsule design led directly to the lightweight liquid field compasses of today.
History of non-navigational uses. Building orientation.
Evidence for the orientation of buildings by the means of a magnetic compass can be found in 12th century Denmark. 1/4 of its 570 Romanesque churches are rotated by 5 to 15 degrees clockwise from true east-west, thus corresponding to the predominant magnetic declination of the time of their construction. Most of these churches were built in the 12th century, indicating a fairly common usage of magnetic compasses in Europe by then.
Mining.
The use of a compass as a direction finder underground was pioneered by the Tuscan mining town Massa, where floating magnetic needles were employed for determining tunneling and defining the claims of the various mining companies as early as the 13th century. In the second half of the 15th century, the compass became standard equipment for Tyrolean miners. Shortly afterwards the first detailed treatise dealing with the underground use of compasses was published by a German miner Ulein von Calw, 1463–1525.
Astronomy.
3 astronomical compasses meant for establishing the meridian were described by Peter Peregrinus in 1269, referring to experiments made before 1248. In the 1300s, an Arabic treatise written by the Egyptian astronomer and Muezzin ibn Simon describes a dry compass for use as a Qibla indicator to find the direction to Mecca. Ibn Simon's compass, however, did not feature a compass card nor the familiar glass box. In the 14th century, the Syrian astronomer and timekeeper Ibn al-Shatur, 1304–1375, invented a timekeeping device incorporating both a universal sundial and a magnetic compass. He invented it for the purpose of finding the times of Salat prayers. Arab navigators also introduced the 32-point compass rose during this time.
Modern compasses.
Modern compasses usually use a magnetized needle or dial inside a capsule completely filled with a liquid, lamp oil, mineral oil, white spirits, purified kerosene, or ethyl alcohol is common. While older designs commonly incorporated a flexible rubber diaphragm or airspace inside the capsule to allow for volume changes caused by temperature or altitude, some modern liquid compasses utilize smaller housings and/or flexible capsule materials to accomplish the same result. The liquid inside the capsule serves to dampen the movement of the needle, reducing oscillation time and increasing stability. Key points on the compass, including the north end of the needle, are often marked with phosphorescent, photoluminescent, or self-luminous materials to enable the compass to be read at night or in poor light. As the compass fill liquid is non-compressible under pressure, many ordinary liquid-filled compasses will operate accurately underwater to considerable depths. Many modern compasses incorporate a baseplate and protractor tool, and are referred to variously as orienteering, baseplate, map compass, or protractor designs. This type of compass uses a separate magnetized needle inside a rotating capsule, an orienting box, or gate for aligning the needle with magnetic north, a transparent base containing map orienting lines, and a bezel, outer dial, marked in degrees or other units of angular measurement. The capsule is mounted in a transparent base plate containing a direction of travel, DOT, indicator for use in taking bearings directly from a map. Other features found on modern orienteering compasses are map and Romer scales for measuring distances and plotting positions on maps, luminous markings on the face or bezels, various sighting mechanisms, mirror, prism, etc. for taking bearings of distant objects with greater precision, global needles for use in differing hemispheres, adjustable declination for obtaining instant true bearings without resort to arithmetic, and devices such as clinometers for measuring gradients. The sport of orienteering has also resulted in the development of models with extremely fast settling and stable needles for optimal use with a topographic map, a land navigation technique known as terrain association. The military forces of a few nations, notably the United States Army, continue to issue field compasses with magnetized compass dials or cards instead of needles. A magnetic card compass is usually equipped with an optical, lensatic, or prismatic sight, which allows the user to read the bearing or azimuth off the compass card while simultaneously aligning the compass with the objective. See photo. Magnetic card compass designs normally require a separate protractor tool in order to take bearings directly from a map. The US M1950 military lensatic compass does not use a liquid-filled capsule as a damping mechanism, but rather electromagnetic induction to control oscillation of its magnetized card. A deep well design is used to allow the compass to be used globally with a card tilt of up to 8 degrees without impairing accuracy. As induction forces provide less damping than liquid-filled designs, a needle lock is fitted to the compass to reduce wear, operated by the folding action of the rear sight lens holder. The use of air-filled induction compasses has declined over the years, as they may become inoperative or inaccurate in freezing temperatures or extremely humid environments due to condensation or water ingress. Some military compasses, like the US M1950, CAMGA 3 hours, military lensatic compass, the silver 4B militaire, and the SWAN 2M5N-T, contain the radioactive material tritium, 1Au3, and a combination of phosphors. The US M1950 equipped with self-luminous lighting contains 120 marci, millicuries, of tritium. The purpose of the tritium and phosphors is to provide illumination for the compass, via radioluminescent tritium illumination, which does not require the compass to be recharged by sunlight or artificial light. However, tritium has a half-life of only about 12 years, so a compass that contains 120 marci of tritium when new will contain only 60 when it is 12 years old, 30 when it is 24 years old, and so on. Consequently, the illumination of the display will fade. Mariners' compasses can have 2 or more gimbaled magnets permanently attached to a compass card. These move freely on a pivot. A lubber line, which can be a marking on the compass bowl or a small fixed needle, indicates the ship's heading on the compass card. Traditionally, the card is divided into 32 points, known as rooms, although modern compasses are marked in degrees rather than cardinal points. The glass-covered box, or bowl, contains a suspended gimbal within a binnacle. This preserves the horizontal position.
Thumb compass.
A thumb compass is a type of compass commonly used in orienteering, a sport in which map reading and terrain association are paramount. Consequently, most thumb compasses have minimal or no degree markings at all, and are normally used only to orient the map to magnetic north. Thumb compasses are also often transparent so that an orienteer can hold a map in the hand with the compass and see the map through the compass.
Gyrocompass.
A gyrocompass is similar to a gyroscope. It is a non-magnetic compass that finds true north by using an electrically powered, fast-spinning wheel and friction forces in order to exploit the rotation of the Earth. Gyrocompasses are widely used on ships. They have 2 main advantages over magnetic compasses. They find true north, that is, the direction of Earth's rotational axis, as opposed to magnetic north. They are not affected by ferromagnetic metal, including iron, steel, cobalt, nickel, and various alloys, in a ship's hull. No compass is affected by non-ferromagnetic metal, although a magnetic compass will be affected by any kind of wires with electric current passing through them. Large ships typically rely on a gyrocompass, using the magnetic compass only as a backup. Increasingly, electronic flux gate compasses are used on smaller vessels. However, magnetic compasses are still widely in use as they can be small, use simple reliable technology, are comparatively cheap, often easier to use than GPS, require no energy supply, and unlike GPS, are not affected by objects, for example trees, that can block the reception of electronic signals.
Solid-state compasses.
Small compasses found in clocks, mobile phones, and other electronic devices are solid-state compasses, usually built out of 2 or 3 magnetic field sensors that provide data for a microprocessor. The correct heading relative to the compass is calculated using trigonometry. Often, the device is a discrete component which outputs either a digital or analog signal proportional to its orientation. This signal is interpreted by a controller or microprocessor and used either internally, or sent to a display unit. The sensor uses highly calibrated internal electronics to measure the response of the device to the Earth's magnetic field. GPS receivers using 2 or more antennae can now achieve 0.5 degree heading accuracy and have startup times in seconds rather than hours for gyrocompass systems. Manufactured primarily for maritime applications, they can also detect pitch and roll of ships.
Specialty compasses.
Apart from navigational compasses, other specialty compasses have also been designed to accommodate specific uses. These include Qibla compass, which is used by Muslims to show the direction to Mecca for prayers, optical or prismatic hand-bearing compass, most often used by surveyors, but also by cave explorers, foresters, and geologists. This compass ordinarily uses a liquid-damped capsule and magnetized floating compass dial with an integral optical, direct or lensatic, or prismatic sight, often fitted with built-in photoluminescent or battery-powered illumination. Using the optical or prism sight, such compasses can be read with extreme accuracy when taking bearings to an object, often to fractions of a degree. Most of these compasses are designed for heavy-duty use, with high-quality needles and jeweled bearings, and many are fitted for tripod mounting for additional accuracy. Trough compasses, mounted in a rectangular box whose length was often several times its width, date back several centuries. They were used for land surveying, particularly with plane tables.
Limitations of a magnetic compass.
The compass is very stable in areas close to the equator, which is far from magnetic north. As the compass is moved closer and closer to one of the magnetic poles of the Earth, the compass becomes more sensitive to crossing its magnetic field lines. At some point close to the magnetic pole, the compass will not indicate any particular direction but will begin to drift. Also, the needle starts to point up or down when getting closer to the poles, because of the so-called magnetic inclination. Cheap compasses with bad bearings may get stuck because of this and therefore indicate a wrong direction. Magnetic compasses are influenced by any fields other than Earth's. Local environments may contain magnetic mineral deposits and artificial sources such as MRIs, large iron or steel bodies, electrical engines or strong permanent magnets. Any electrically conductive body produces its own magnetic field when it is carrying an electric current. Magnetic compasses are prone to errors in the neighborhood of such bodies. Some compasses include magnets which can be adjusted to compensate for external magnetic fields, making the compass more reliable and accurate. A compass is also subject to errors when the compass is accelerated or decelerated in an airplane or automobile. Depending on which of the Earth's hemispheres the compass is located and if the force is acceleration or deceleration, the compass will increase or decrease the indicated heading. Compasses that include compensating magnets are especially prone to these errors, since accelerations tilt the needle, bringing it closer or further from the magnets. Another error of the mechanical compass is turning error. When one turns from a heading of east or west, the compass will lag behind the turn or lead ahead of the turn. Magnetometers, and substitutes such as gyrocompasses, are more stable in such situations.
Construction of a compass. Magnetic needle.
A magnetic rod is required when constructing a compass. This can be created by aligning an iron or steel rod with Earth's magnetic field and then tempering or striking it. However, this method produces only a weak magnet, so other methods are preferred. For example, a magnetized rod can be created by repeatedly rubbing an iron rod with a magnetic lodestone. This magnetized rod, or magnetic needle, is then placed on a low-friction surface to allow it to freely pivot to align itself with the magnetic field. It is then labeled so the user can distinguish the north-pointing from the south-pointing end. In modern convention, the north end is typically marked in some way.
Needle and bowl device.
If a needle is rubbed on a lodestone or other magnet, the needle becomes magnetized. When it is inserted in a cork or piece of wood, and placed in a bowl of water, it becomes a compass. Such devices were universally used as compass until the invention of the box-like compass with a dry pivoting needle sometime around 1300.
Points of the compass.
Originally, many compasses were marked only as to the direction of magnetic north, or to the 4 cardinal points, north, south, east, west. Later, these were divided, in China into 24, and in Europe into 32 equally spaced points around the compass card. For a table of the 32 points, see compass points. In the modern era, the 360-degree system took hold. This system is still in use today for civilian navigators. The degree system spaces 360 equidistant points located clockwise around the compass dial. In the 19th century, some European nations adopted the grad, also called grade or gon, system instead, where a right angle is 100 grads to give a circle of 400 grads. Dividing grads into tenths to give a circle of 4,000 decigrades has also been used in armies. Most military forces have adopted the French millième system. This is an approximation of a milliradian, 6283 per circle, in which the compass dial is spaced into 6400 units or mils for additional precision when measuring angles, laying artillery, etc. The value to the military is that one angular mil subtends approximately 1 meter at a distance of 1 kilometer. Imperial Russia used a system derived by dividing the circumference of a circle into chords of the same length as the radius. Each of these was divided into 100 spaces, giving a circle of 600. The Soviet Union divided these into tenths to give a circle of 6,000 units, usually translated as mils. This system was adopted by the former Warsaw Pact countries, Soviet Union, GDR etc., often counterclockwise. See picture of wrist compass. This is still in use in Russia.
Compass balancing magnetic dip.
Because the Earth's magnetic field's inclination and intensity vary at different latitudes, compasses are often balanced during manufacture so that the dial or needle will be level, eliminating needle drag which can give inaccurate readings. Most manufacturers balance their compass needles for one of 5 zones, ranging from Zone 1, covering most of the Northern Hemisphere, to Zone 5 covering Australia and the Southern Oceans. This individual zone balancing prevents excessive dipping of one end of the needle which can cause the compass card to stick and give false readings. Some compasses feature a special needle balancing system that will accurately indicate magnetic north regardless of the particular magnetic zone. Other magnetic compasses have a small sliding counterweight installed on the needle itself. This sliding counterweight, called a rider, can be used for counterbalancing the needle against the dip caused by inclination if the compass is taken to a zone with a higher or lower dip.
Compass correction.
Like any magnetic device, compasses are affected by nearby ferrous materials, as well as by strong local electromagnetic forces. Compasses used for wilderness land navigation should not be used in proximity to ferrous metal objects or electromagnetic fields, car electrical systems, automobile engines, steel pitons, etc. as that can affect their accuracy. Compasses are particularly difficult to use accurately in or near trucks, cars or other mechanized vehicles even when corrected for deviation by the use of built-in magnets or other devices. Large amounts of ferrous metal combined with the on and off electrical fields caused by the vehicle's ignition and charging systems generally result in significant compass errors. At sea, a ship's compass must also be corrected for errors, called deviation, caused by iron and steel in its structure and equipment. The ship is swung, that is rotated about a fixed point while its heading is noted by alignment with fixed points on the shore. A compass deviation card is prepared so that the navigator can convert between compass and magnetic headings. The compass can be corrected in 3 ways. First, the lubber line can be adjusted so that it is aligned with the direction in which the ship travels, then the effects of permanent magnets can be corrected for by small magnets fitted within the case of the compass. The effect of ferromagnetic materials in the compass's environment can be corrected by 2 iron balls mounted on either side of the compass binnacle. The coefficient representing the error in the lubber line, while the ferromagnetic effects and the non-ferromagnetic component. A similar process is used to calibrate the compass in light general aviation aircraft, with the compass deviation card often mounted permanently just above or below the magnetic compass on the instrument panel. Flux gate electronic compasses can be calibrated automatically, and can also be programmed with the correct local compass variation so as to indicate the true heading.
Using a compass.
A magnetic compass points to magnetic North Pole, which is approximately 1,000 miles from the true geographic North Pole. A magnetic compass's user can determine true north by finding the magnetic north and then correcting for variation and deviation. Variation is defined as the angle between the direction of true, geographic, north and the direction of the meridian between the magnetic poles. Variation values for most of the oceans had been calculated and published by 1914. Deviation refers to the response of the compass to local magnetic fields caused by the presence of iron and electric currents. One can partly compensate for these by careful location of the compass and the placement of compensating magnets under the compass itself. Mariners have long known that these measures do not completely cancel deviation. Hence, they performed an additional step by measuring the compass bearing of a landmark with a known magnetic bearing. They then pointed their ship to the next compass point and measured again, graphing their results. In this way, correction tables could be created, which would be consulted when compasses were used when traveling in those locations. Mariners are concerned about very accurate measurements. However, casual users need not be concerned with differences between magnetic and true north. Except in areas of extreme magnetic declination variance, 20 degrees or more, this is enough to protect from walking in a substantially different direction than expected over short distances, provided the terrain is fairly flat and visibility is not impaired. By carefully recording distances, time or paces, and magnetic bearings traveled, one can plot a course and return to one starting point using the compass alone. Compass navigation in conjunction with a map, terrain association, requires a different method. To take a map bearing or true bearing, a bearing taken in reference to true, not magnetic north, to a destination with a protractor compass, the edge of the compass is placed on the map so that it connects the current location with the desired destination. Some sources recommend physically drawing a line. The orienting lines in the base of the compass dial are then rotated to align with actual or true north by aligning them with a marked line of longitude, or the vertical margin of the map, ignoring the compass needle entirely. The resulting true bearing or map bearing may then be read at the degree indicator or direction of travel, DOT, line, which may be followed as an azimuth, course, to the destination. If a magnetic north bearing or compass bearing is desired, the compass must be adjusted by the amount of magnetic declination before using the bearing so that both map and compass are in agreement. In the given example, the large mountain in the second photo was selected as the target destination on the map. Some compasses allow the scale to be adjusted to compensate for the local magnetic declination. If adjusted correctly, the compass will give the true bearing instead of the magnetic bearing. The modern handheld protractor compass always has an additional direction of travel, DOT, arrow or indicator inscribed on the base plate. To check one's progress along a course or azimuth, or to ensure that the object in view is indeed the destination, a new compass reading may be taken to the target if visible, here, the large mountain. After pointing the DOT arrow on the base plate at the target, the compass is oriented so that the needle is superimposed over the orienting arrow in the capsule. The resulting bearing indicated is the magnetic bearing to the target. Again, if one is using true, or map bearings, and the compass does not have preset, pre-adjusted declination, one must additionally add or subtract magnetic declination to convert the magnetic bearing into a true bearing. The exact value of the magnetic declination is place-dependent and varies over time, though declination is frequently given on the map itself or obtainable online from various sites. If the hiker has been following the correct path, the compass-corrected, true, indicated bearing should closely correspond to the true bearing previously obtained from the map. A compass should be laid down on a level surface so that the needle only rests or hangs on the bearing fused to the compass casing. If used at a tilt, the needle might touch the casing on the compass and not move freely, hence not pointing to the magnetic north accurately, giving a faulty reading. To see if the needle is well leveled, look closely at the needle, and tilt it slightly to see if the needle is swaying side to side freely and the needle is not contacting the casing of the compass. If the needle tilts to one direction, tilt the compass slightly and gently to the opposing direction until the compass needle is horizontal, lengthwise. Items to avoid around compasses are magnets of any kind and any electronics. Magnetic fields from electronics can easily disrupt the needle, avoiding it from pointing with the Earth's magnetic fields, causing interference. The Earth's natural magnetic forces are considerably weak, measuring at 0.5 Gauss, and magnetic fields from household electronics can easily exceed it, overpowering the compass needle. Exposure to strong magnets, or magnetic interference, can sometimes cause the magnetic poles of the compass needle to differ or even reverse. Avoid iron-rich deposits when using a compass, for example, certain rocks which contain magnetic minerals, like magnetite. This is often indicated by a rock with a surface which is dark and has a metallic luster. Not all magnetic mineral-bearing rocks have this indication. To see if a rock or an area is causing interference on a compass, get out of the area, and see if the needle on the compass moves. If it does, it means that the area or rock the compass was previously at on is causing interference and should be avoided.